We are starting our next unit, Exploring the Universe! And we are going to kick things off talking about units in space. So, when we're talking about different things like celestial bodies, aka any sort of object that is located in space, we often talk about how far or how close they are from us or from each other. So, when we're talking about these distances, it doesn't quite make sense to use the same distances as we would here when describing distances on Earth. We're not going to say, oh yeah, the sun is this many meters away, or this many kilometers away, or maybe even this many miles if we're talking in the imperial system. We have to have some units that are much larger, so we don't have to use larger numbers. So we're going to talk about 3 different types of units that are commonly used when talking about distance in space. The first one is called an astronomical unit, and it is abbreviated, by the capital letter AU, standing for astronomical unit. What they say is 1 astronomical unit is the average distance from the sun to the Earth. And we say average distance because, as we know, the Earth is always revolving around the sun. And as it does its revolution, it's not a complete perfect circle. So sometimes it's a little bit closer to the sun, sometimes it's a little bit further. But on average, the Earth is 1 astronomical unit away from the Earth. We create that as our baseline. So if that's 1, then the distance from Sun to Mars is 1.52, right? So it's about 1.5 times as far as the Sun to the Earth. If we wanted to see, what would that mean in our normal units, we could say 1 astronomical unit is 149,600,000,000 meters, or 149,600,000 kilometers, which is a huge number. We can write that number in scientific notation, and we're going to actually be learning how to use scientific notation down the road, but it can be represented by saying 1.496 times 10 to the power of 11 meters. So that's astronomical unit. That's our first unit. If you wanted to look at the distances from the sun, we can see here we have Earth, and that's 1 astronomical unit. Mars was 1.52, if we remember from the previous slide. But we can see Jupiter's about 5, Saturn's about 10, Uranus is about 20, and Neptune's about 30. And then, of course, Mercury and Venus here are going to be less than 1. Right? So, just in case we want to see how the other planets differed in terms of their distance from the sun. If Earth is 1 and Jupiter is 5, we could say the distance between Earth and Jupiter is going to be 4. It's the difference between the two of them. Anyway, something pretty cool. And that is an idea of an astronomical unit. The next one that we're going to be talking about is something called a light year. And a light year is a unit of measurement for distance, not time. So many people confuse light years for a time measurement, and that's a really common mistake that's made. Because when you think year, you think of time, right? Like, how long have you lived? I've lived 14 years. That's a unit of time. But when we're talking about a light year, that is going to be a unit of distance, not time. Well, that unit of distance is defined as how far light will travel in the period of 1 year. And that's a really, really large distance, because just for reference here, every single second, light can travel 299,792,458 meters. That's every single second. That's how far light can travel, which is ridiculously fast. So to say what is a light year, well, a light year in terms of meters is 9,460,730,000,000 472,580,000 meters. Holy Toledos! Right? That's why we're not using meters when we could just say, yeah, it's just 1 light year. So that is absolutely insane. That is how far light can travel in 1 year. That number can be also written in scientific notation as 9.46072 times 10 to the power of 15 meters. And again, like I said at the end of this lesson, we're going to be learning how to... boop, boop, boop. This should be a 3. Silly notes package. All right. But we're going to be learning how to do scientific notation by the end of today's lesson. It's going to be dope. If we're just trying to look at how far light will travel, just again for reference, from Earth to the moon, if we want to see the light that's reflecting off the moon on Earth, it takes 1.29 light seconds for that light to travel to Earth. Or that's the distance between the Earth and the moon. The distance between the sun and the Earth is 8 light minutes. So light takes 8 minutes to travel to Earth. So the distance is 8 light minutes, which is kind of cool because if something were ever to happen to the sun and say maybe that light is no longer visible to us, maybe the sun just explodes or something like that, we won't notice for 8 minutes. Because it takes that long for that light to travel from the sun to the Earth, because that is a large amount of distance that light needs to travel through. From Earth to Mars, it's 12.7 light minutes. That's the distance. For the nearest star other than the sun, which is called Proxima, it actually takes 4.3 light years from Earth. That's the distance that it travels between our Earth and that star. And then Earth is part of the Milky Way galaxy, which is absolutely huge. And the distance from Earth to the other side of that galaxy is 52,000 light years, which is, again, insane. So those are the distances which we can see between the Earth and some of the other celestial bodies in our universe. Now, the last unit that we're going to be talking about is the parsec. Okay? So a parsec is a distance of 30 quadrillion 857 trillion meters, which is, again, a huge distance. The way or the reason that we use a parsec, it's derived from something called an arc second, which is actually how far stars appear to move in the sky over a period of 6 months. Okay, so that is how that unit was derived. You won't need to know the specific of where that came from, but that unit is commonly used when talking about distances in space. Again, that distance can be written in scientific notation when we're talking about that value in terms of meters, and that can be written as 3.0857 times 10 to the power of 16 meters. Alrighty, the time and the moment we have all been waiting for. Scientific notation. Whoop, whoop. Love it. So, what scientific notation is, it's really just a standardized way of representing really, really big numbers or really, really small numbers so that they're easier either to compare or to use in calculations or computations. Okay? This is the all-time pattern or the setup that you'll see in scientific notation. We will have some number n times 10 to the power of some number. Okay? There's a couple of specific things that have to happen when we're talking about scientific notation. So our n can vary from number to number, and our a can vary from number to number. But we will always have times 10 involved in some way, shape, or form. Okay? When we're talking about n has to follow this rule. It has to be a number between 1 and 10 but it can't be 10 itself. So n can be 1.23456, n could be 5.47, n can be 9.99999, but it can't be 10. So any number that is 1 or larger, but it has to be less than 10. Okay. N could also be whole numbers, so n can be like, 4. It could be 1. It could be 8. But it could also have decimals involved. When we're talking about our exponent, this a value here, a has to be an integer. So it has to be either a positive or negative whole number. Okay, so a has to be 1, 2, 3, 4, 5, or so on, or 0, -1, -2, -3, -4, and so on, right? It can't have any decimals related to it. So n itself can be a decimal between 1 and 10, not including 10, and a has to be an integer, so a positive or negative whole number, so no decimals involved. Okay. Now let's figure out how to write numbers in scientific notation. There's 3 steps to it. Step 1 is we're going to look at the number that we have, and we're going to determine where that decimal place is currently located. We are then going to take that decimal place and move it over until we have a number between 1 and 10. Get that n value. Okay. Step 2 is we are going to determine our exponent. This is the number of times that we've moved the decimal place over. So if we've moved it 4 times, our exponent is going to be 4. But the question is it going to be positive or is it going to be negative? If we've moved the decimal place to the left, the exponent is going to be positive. If you move the decimal place to the right, the exponent is going to be negative. The last thing that we're going to do, because we've determined n, and then we've determined a in step 2, was we are going to rewrite it in scientific notation form. So step 1 is to find n, step 2 is to find a. And we're going to look at some examples to make sure that we're all on the same page, because this could sound a little bit tricky. All right, so we're going to look at this first example here. We have 547 million. Big number. Okay, when we are looking at this number, we don't see a decimal place right now. I don't see a little point anywhere. But that decimal place is always going to be located at the very end of our number unless it's otherwise indicated in our value. So our decimal place is over there. We have to move this decimal place either to the left or to the right. Okay. If we move it to the right, there's no numbers over there, so that's not really going to help us. So we are going to move it to the left. So we're going to move it over until we have a value that is between 1 and 10. And so if we move it over here, do we have a value between 1 and 10? No, we have this, and that number is still huge. We're going to keep on moving it. If we move it all the way over here, our number is going to be 547. If we move it over one more, we get 54.7. If we move it over one more, we get 5.470000000. Okay, so we are going to move it until essentially there is only one number that isn't 0 to the left of that decimal place. Okay, so we have 5 that's to the left of this decimal place and every other number to the right. So that is step 1. Our n value is going to be 5.47. We could write all of these zeros, but it's actually unnecessary if we write them after this decimal place. So we will have 5.47 as our n value here. Our next step, so that was step 1. Step 2 is to figure out how many times we've moved it. So we've moved it 1, 2, 3, 4, 5, 6, 7, 8 times, right? The decimal used to be over here, and we moved it all the way over there. We've moved it across 8 different numbers. So our a value is going to be 8. But is it going to be a positive or is it going to be a negative? Well, we moved our decimal. It started over here and ended over here. We moved it to the left, which means we are going to have a positive exponent. So our a value is going to be positive 8. Our last step is to rewrite that number in scientific notation form. So we have n, which is 5.47, times 10 to the power of a, which is positive 8. So our value of 547 million will end up as 5.47 times 10 to the power of 8. Okay, so step 1 was finding n, step 2 was finding a, step 3 is our final answer here. What you will notice as a pattern when you're thinking of, if I'm moving numbers to the left, if you have a big number to begin with, so any number bigger than 10 or 10 or bigger is considered a big number. If you have a big number to begin with, and 547 million is a big number, you are going to end up with a positive exponent. If you have a small number, and a small number can be any number that's smaller than 1. So I'll say bigger than 10. And a small number will be smaller than 1. Then you will have a negative exponent. That's another way that you could help remember, is my exponent positive or negative? And we're going to take a look and see what happens when we have a small number. I'm going to erase this here. And we are going to look at this next number. We have 0.000098. Okay. So that is our next example here. For step 1, we are trying to determine our n value. We're looking at where our decimal is now, and our decimal is located right here. And we are going to move it over until we have a number between 1 and 10. Essentially, so we only have one value that is not a 0 to the left of our decimal place. So I'm going to move it over to the right. 1, 2, 3, 4, 5. And I will end up with 9.8. So my n value is going to be 9.8. Because again, we only have one number that is not 0 to the left of my new location of my decimal place. All right. Step 2. We are going to look for our a value. And remember, our a value is how many times we moved our decimal over. So we've moved it 1, 2, 3, 4, 5 times. So we're going to have a is equal to 5. And is it a positive or a negative? Well, we did move the decimal place. We started over here, ended over here. We moved it to the right. So it will end up being a negative 5. Or we could think of, well, that number that we began with, that 0.000098, was a number that is smaller than 1. It is a small number. Since it's a small number, we could also remember that that exponent is going to be negative. Our last step is going to be to put those two together. So we end up with n, which is 9.8, times 10 to the power of a, which is negative 5. So there you have it. There's some examples on the next slide here, right under your notes there, that I'd like you to give a try. If you could, can you please pause this video real quick and go ahead and try these on your own, and then press play when you're feeling like you're ready. Okay? Pause. Did you do it? I hope so. Let's go over some answers together. We're going to go through them a little bit quicker, but nothing too crazy. So, the first number here, we have 67,200,000. 67,200,000. Our decimal starts on the very end here because it's not otherwise written inside of our examples. And we are trying to figure out our n value. My n value is determined by moving that decimal over until I only have one number that isn't a 0 to the left of my decimal. So I'm going to be moving it 1, 2, 3, 4, 5, 6, 7 times until I get 6.72. My a value, like I said, we moved it 7 times, so I'm going to have a 7. Is that going to be a positive or a negative? Well, I moved my decimal over to the left, so it's going to be a positive exponent. Or I could think, well, hey, this number 67,200,000 is a very big number. Big numbers are going to have positive exponents in terms of scientific notation. So my final answer will be 6.72 times 10 to the power of 7. My next example, I have 0.005981. My decimal starts over here. I am going to move it to the right until I only have one number that is not a 0 to the left of my decimal place. So I'm going to move it over 1, 2, 3 times to the right. So my n is going to be 5.981. My a value, I said I moved it over 3 times. So it's going to be a 3. Is it going to be positive or negative? Well, I moved that decimal over to the right, so it's going to be negative. Or I could just think, well, hey, that number 0.005981 is a small number. Small numbers will have scientific notation with a negative exponent. So my final answer, when I put my n and a together in scientific notation, I get 5.981 times 10 to the negative 3. I realized I wanted to do this in a different color, but did not. Oops. Okay. Next, I have 0.000233418. I'm going to start by looking where my decimal is. Oh, there she is. And I'm going to be moving it until I have only one value that is not a 0 to the left of my decimal place. So I am moving it to the right 1, 2, 3, 4 times. That gives me an n value of 2.34, that 3 is kind of ugly, 3418, and an a value of 4. Is it positive or negative? Well, that number is ridiculously small. It is smaller than 1 to begin with. So I am going to say that is a negative exponent. Small numbers get scientific notation with negative exponents. So my final answer is going to be 2.3418 times 10 to the power of negative 4. We'll put these maybe in boxes so that it's more obvious to tell where the answers are. Next one here, we have 17. Where is that decimal located? Oh, there she is, right out there. We are going to move it until we only have one number that is not a 0 to the left of my decimal place. So I have to move it over 1 time. And I'm moving it over 1 time to the left. My n is going to be 1.7 now. My a is going to be 1. Is it going to be a positive or a negative? Well, 17 is a number that is bigger than 10, which means I'm going to have a positive a value, or I move my decimal over to the left, so it's a positive a value, so I will end up as 1.7 times 10 to the power of 1. All right. I'm going to scroll down here to the next slide because they will show you, or that slide will show the answers to the last 3 over here. So if you pause on this screen, you will see all of the answers to all of the examples that you would have tried. Okay, so here, if I'm looking at this example, at 6,325, my decimal is here. I moved it over 1, 2, 3, so I get 6.325. I've moved it over 3 times. 6,325 is a big number, so that exponent is positive. If I look at my next example, my 0.9, I'd have to move my decimal over 1, so I get 9. And because 0.9 is a small number to begin with, it's smaller than 1, I have a negative exponent. So I have 9 times 10 to the power of negative 1. If I look at my last example here, I'm going to be moving my decimal over 2 times until I get 2.004. I've moved it 2 times to the right. My original number was small, so I will have a negative exponent. So I have 2.004 times 10 to the negative 2. When you are converting to scientific notation, I do not need to see all of your work and saying, what is your n value, what is your a value. You just need to show me how to get from here to here. However, if you feel more comfortable writing what that n value is or writing what that a value is, then by all means, that is a-okay. I know personally, I always show how many bumps I have so that I can count them after, and that's essentially the extent of my work. But do what you feel is best for you. All right, we've learned how to convert to scientific notation. It might actually be useful to learn how to convert back too, because sometimes we could be giving you values in scientific notation, or eventually maybe your calculators one day give you numbers in scientific notation. It is meaningful to know what that represents in terms of standard numbers, or in numbers in standard form. So, what we are going to do is we have 2 steps, okay? Step 1 is what we're going to be doing is we're going to be determining the direction of travel of our decimal place. And that depends on my exponent. If my exponent is positive, I'm going to be moving my decimal to the right. And if my exponent is positive, I should end up with a big number. So a number greater than 10. If my exponent is negative, you want to move your decimal to the left. I want to end up with a small number. Okay, so it's essentially undoing what we did before. And so that's just determining the direction that we're going to be moving the decimal. Are we going to move the decimal to the right? Are we going to move the decimal to the left? And step 2 here is we're going to move that decimal in the desired direction. The amount of times as my exponent. So if my exponent is 7, I'm going to move it 7 times. If my exponent is -8, I'm going to move the decimal 8 times. Okay? The negative or the positive on that exponent just tells me which way am I moving it. So if I have a positive 7, I'm going to move it to the right 7 times. If I have a -8, I'm going to be moving the decimal to the left 8 times. Let's try it out. So first example here, I have 6.11 times 10 to the -9. Okay. I have a negative exponent here, so I'm going to be moving my decimal to the left, which kind of makes sense because I want to end up with a small number, because small numbers will end up with scientific notation with a negative exponent, so I want to end up with a small number. If I'm moving it to the left, I need to move it how many times? I have to move it 9 times. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. And then draw my decimal there. I am then going to fill in all those spots with zeros. So 1, 2, 3, 4, 5, 6, 7, 8. And then a 0 to begin with. So I'm going to rewrite this answer here as 0 decimal 1, 2, 3, 4, 5, 6, 7, 8, 6, 1, 1. This is what I'm going to end up with here. So I've moved my decimal over from this location here to this location there. Okay? If I've moved this decimal over, that decimal is now gone. And I am just rewriting my final answer that I have up above without the times 10 to the power of -9. So I essentially get the exact same thing there. Oops, there you go. All right. Notice that my final answer is a small number. It's a number that's smaller than 1, which makes sense because it had a negative exponent. And just like we talked about before, if we have the exponent is negative, it should be because there's a small number, and that number is smaller than 1. Right? So we could see that connection there. All right. The next example that we can do is we have 1.278 times 10 to the 12. Our exponent is positive, which means we are going to be moving our decimal to the right, and we should end up with a big number. Okay, so if we move our decimal to the right, we could see our decimals here right now. How many times we're moving it? We're moving it 12 times. Move this arrow over. So we're going to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we're going to fill out all those gaps with zeros after. So if I'm looking at this guy, I could essentially take my spots and fill them with zeros. Doop, 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 doop. To get 1, 2, 7, 8, 0, 0, 0, 0, 0, 0, 0, 0, 0, and my decimal ends up at the end there. Okay. So my original question of 1.278 times 10 to the positive 12 will end up as 1,278,000,000,000. Right, because we've moved it over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times. Okay. Alrighty. Here are some examples that you could try on your own. I'd like you to pause the video, give it a go. And then when you come back, we could review some of those together, and I'll show you the answers to the rest. And pause! And welcome back! Alright, we have a couple examples that we're going to do together. So our first one here is we have 7.942 times 10 to the negative 4. My exponent is negative, which means I should end up with a smaller number. So I'm going to be moving my decimal to the left. How many times am I going to do that? I'm moving it over 4 times. So I'm going to go 1, 2, 3, 4. Here's my new decimal. And I'm going to fill in the spots with 0. So I will end up with 0.000792. My next question, I have 1.2 times 10 to the power of 3. My exponent is positive, which means I am moving my decimal over to the right. Because I have a positive exponent, I should end up with an answer that's a big number. Okay, so I'm moving it over how many times? 3. 1, 2, 3. I'm filling in all those bumps with zeros. And so I should end up with 1, 2, 0, 0 as my final answer here. So 1,200. My next dude, I've got 5.06 times 10 to the power of 1. My exponent is positive. I am moving that decimal over to the right, so I should end up with a bigger number. How many times am I moving it? I'm only moving it once, so I move it over there. So I end up with a final number as 50.6. Notice that I do not have any gaps or bumps to fill with zeros in this case. That is a-okay. I'm only filling in with zeros if I have more bumps to spare. Next guy, up in here, I get 8. I have 8.0019 times 10 to the negative 7. My exponent is negative, which means I should end up with a smaller number. And I am moving my decimal over to the left. How many times am I moving it? 7. So it starts here, and I go 1, 2, 3, 4, 5, 6, 7. Here's my decimal. And I'm filling in all those bumps with zeros. So I end up with 0.0000000800019. All right, the last 3 here, I'm going to show you the answers to on the next slide here. And here we have it, folks. I guess we didn't have to zoom in. So here are the answers to the last 3 questions. And again, you do not have to necessarily show me the work. You just have to show me the final answer. I know when I go ahead and show or try and do these questions, I do show the little bumps. So if I was doing this example here, I could see I have 3.48 times 10 to the power of 12. I'm moving it 12 to the right to end up with a big number. And I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then I fill them. They're missing spots with 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I need 10 zeros in this case. And here I have 3, 6, 9, 10. And then my original number. Same thing with all of the other questions. You don't have to show your work, but if you'd like to, you're more than welcome to. Alrighty. Little reminder here, don't forget that small numbers, numbers that are less than 1 will have negative exponents in scientific notation. And large numbers, there's a little typo here, numbers greater than 10 will end up with positive exponents. Alright, that's it for scientific notation. Hope you learned lots, and I hope you practice lots because there will be some sort of assessment coming up soon. All right, adios, muchachos.